Okay.
Just a minute. Okay, so welcome everybody to this session of our seminar. This is the last session of the academic year. So it's for me really a pleasure to introduce Jean-Pierre Puel for this final session of the seminar. He will talk about from distributed controllability to boundary controllability. So Jean-Pierre, thank you.
Thank you very much for the invitation. And sorry for, hello everybody, but sorry for the delay due to my incompetence in Zoom. Okay. Okay, I will talk about this problem of going from distributed controllability to boundary controllability. And well, it is essentially the same talk I gave in Bordeaux in December in honor of Marius Tuxnack. So I apologize for those who were already in Bordeaux. You can go and take a coffee. There is no real change. It will be a little bit more technical here. Okay, so I start. Ah, ça marche pas. Okay. Well. Okay, so I consider a problem of distributed controllability with control acting on an epsilon neighborhood of the part of the boundary. And the problem is what happens when epsilon tends to 0? Do we have convergence to a boundary controllability problem? So for notations, omega is the bounded regular open set of Rn, and the boundary is gamma. Q is omega times 0t, and gamma naught is a open, non-empty open subset of gamma. And we take little omega epsilon is the union of, you will see a picture afterwards, union of the, for x in gamma naught of the balls bx epsilon intersect omega. So it's a subset, which is an epsilon neighborhood of gamma naught. Okay. For the wave equation, we worked on this question in the 90s together with Caroline Fabre, and you have the references hereafter. And surprisingly, there was nothing done for the case of the heat equation. And we have written something with two young Brazilian guys, Felipe Chavez Silva and Mauricio Cardoso Santos, for the heat equation. And I will present the results here. So you have also the reference here. Okay, so let's go back to the problem for the wave equation. So we have the wave equation. We have the control acting on an epsilon neighborhood of the boundary of gamma naught, of the part of the boundary, gamma naught. Y is 0, Dirichlet boundary condition. Y is 0 on the whole boundary. Initial condition, Y naught, Y1. And we want to find the control V such that at time t, the wave is stopped. Y at time t is 0, and the velocity dty at time t is 0. So this is a classical problem. In order to solve this problem, we need a geometric condition, saying essentially that every ray of the geometric optics propagating at speed 1 meets omega epsilon before time t. Okay, this is the this is the picture of omega epsilon drawn by me. So it is, I am very bad in drawing pictures. So. Okay. So what happens when epsilon tends to 0? So first of all, for epsilon fixed, the classical way to solve that is the following. So we have to take y0 in h10, and you will see why it is important. This is important. Y0 in h10 and y1 in L2. And we take the adjoint equation, which is, because of the wave equation, it is of the same kind, dtt phi epsilon minus delta y, oh, there is no y, of course, here, minus delta phi epsilon is 0. Phi epsilon is 0 on the boundary, and the initial conditions are phi epsilon naught and phi epsilon 1. And here we take phi epsilon naught in L2, and this is important, and phi epsilon 1 in H minus 1. So phi epsilon is not a solution with finite energy. Okay, it's a weak solution of the wave equation. And we know if you have the geometric condition, we know that we have observability inequality, which is that the norm of phi is epsilon 0 in L2 and phi epsilon 1 in H1 minus 1 square is dominated, is bounded by a constant, which of course depends on epsilon. The integral of phi epsilon square on the set omega epsilon times 0t. Okay, this is classical. The problem is, what is C epsilon? One problem is that. Well, there is no hope to obtain classical estimates as the boundary condition cannot be preserved. Yes. So we have three main difficulties for the problem. Maybe it's not in order, but we can show that when we have this quantity, the norm of phi epsilon square on the set omega epsilon dot 0t divided by epsilon cube, when this is bounded independently of epsilon, and when phi epsilon converges to phi in some sense, in some natural space, then at the limit, you have that the normal derivative of phi is in L2 of gamma naught times 0t. So this is one first difficulty. So this is not given by the equation. Remember that phi epsilon is not a solution of finite energy. So for phi epsilon, we don't know that the normal derivative is in L2. But at the limit, you will have the normal derivative in L2. And moreover, so again, if gamma naught t satisfy the geometric condition, this means that phi, the limit phi, is of finite energy. So the initial data, phi epsilon 0, phi epsilon 1, they converge to something phi 0, phi 1, but these limits are in H10 times L2. Whereas the phi epsilon 0 was in L2, the limit phi 0 is in H10. When the phi epsilon 1 was in H minus 1, the limit phi 1 is in L2. Because you have this this regularity, this result of regularity and the geometric condition. So this is important. Then we have to show that the constant which appears in the observability inequality, C epsilon, satisfies C epsilon is of the order of epsilon minus 3, 1 over epsilon cubed. And then you end up, you come up with a, for epsilon fixed, with a controllability problem where the control can be taken as 1 over epsilon cubed phi epsilon, acting on omega epsilon. And then, so you see, this is the problem when for epsilon fixed. And then you have to pass to the limit in this problem. And we will have the same situation for the heat equation. So for people who are not interested in control, like Lucio Boccardo and so on, this is interesting. You have an operator here, and you have a right-hand side, which is, well, take your regular function, which is 0 on the boundary, phi epsilon. And you take something which is concentrated near the boundary and singular. And you want to pass to the limit. And what you obtain, so I will not give the result for the wave equation. We have to pass to the limit in the wave, in the weak formulation for the wave equation. And at the limit, you obtain 0 on the right-hand side, but you have a non-homogeneous Dirichlet condition. And the Dirichlet condition on gamma naught is minus 1/3 d phi d nu, this limit of phi. And you have the same initial condition, and you can stop the wave at time t. But notice, as you know that phi 0, phi 1 are now in H10 L2, now you can take Y0 weaker in L2 and Y1 weaker in H-1, as it is expected for the boundary control for the wave equation. Okay. Now take the case of the heat equation. Okay, the heat equation, same problem. You have a control concentrated in an epsilon neighborhood of the boundary, 0 on the whole boundary, and initial condition Y0, and you want to stop the value of to drive Y to 0 at time t. Okay. So here it is well known that we do not need any geometric condition. We just need that omega epsilon has to be non-empty open set in omega, and any t positive. And to solve this, again, it is classical. To solve this problem, we use the following observability inequality, which is if you take the adjoint problem, phi, which is now backward in time, minus d phi dt minus delta phi. So this is backward in time, starting at time t to go at time 0 with phi t and 0 on the boundary. We want to show that the value of phi at 0 in L2 square is bounded by the integral of phi square on the set of control omega epsilon times 0t, and of course with a constant which depends on epsilon again. Okay, so this is classical. If you know that, well, you know that you can do that, and this is the way to solve the problem here. The problem is that the usual way to obtain this inequality is to use a global Carleman estimate with a principal positive regular weight. So in Carleman estimates, you have many weights, but you have a principal weight, and from which you construct other weights depending on time and so on. But the principal weight depends only on the space variable. It is positive. It is regular. But usually we take it having 0 on the boundary, or at least a negative normal derivative. And a non-vanishing, the importance is, what is important is that the weight has a non-vanishing gradient in omega minus the set of control. So the only place where the gradient of this weight can vanish is to be inside omega epsilon, where you can act. So therefore, if you have if you draw a picture even in 0, 1, you take a 0 epsilon as omega epsilon, and you have a positive function being 0 at 0 and 0 at 1, and the gradient has to be non-negative, strictly non-vanishing in epsilon 1. So you have a steep gradient in omega epsilon. And there is no hope to obtain sharp estimates on C epsilon directly with this method. No hope. Well, we will show in the next slide that this C epsilon is a gain of the order epsilon minus 3. And this is optimal, and this is the major difficulty of this work. And the passage to the limit afterwards will be treated in an analogous way as for the case of the wave equation. So here we don't have any geometric condition. Gamma naught may be any part of a non-empty part of the boundary. Omega epsilon is the union of balls of radius epsilon and centered in gamma naught. And you can act here, and you want to study what happens when epsilon tends to 0. Okay. So sorry for the technicalities, but we start with we will talk about Carleman estimates. We have to talk with weights. So we have this basic weight that we need, which is C2 in omega bar. So the gradient, now we take the gradient to be non-zero everywhere in omega bar, everywhere, not in omega epsilon, everywhere. And we want the normal derivative of psi to be negative where we are not interested in the control, gamma minus gamma naught. Okay. And with this weight, we construct other weights. So phi, capital phi, is exponential lambda this psi plus a constant m1 over t, capital T minus t. So this will blow up when t tends to 0 and when t tends to capital T. This phi, lambda will be positive, okay, it's positive. And so capital phi tends to plus infinity when t tends to 0, plus infinity when t tends to capital T. And alpha will be, okay, we start with the same quantity, but we have minus exponential lambda norm of psi infinity plus m2, this is a constant, over the same denominator. And we take m1, for example, this is a possibility. M1 is psi infinity plus 2, m2 is psi infinity plus 3. So this guy, this constant, is bigger than this for any x, which says that alpha is negative. Alpha is negative. So alpha tends to minus infinity when t tends to 0, and minus infinity when t tends to capital T. And therefore, for any s positive parameter, there will be another parameter s. If you take exponential 2s alpha, this will tend violently to 0 when t tends to 0 and when t tends to capital T. And if you multiply by phi k, this will again, because here you have an exponential, this will again do the same, tends to 0 when t tends to 0 and t tends to capital T. And these expressions will be uniformly bounded. Okay, so these are the weights. And we start, the problem is that we cannot use a global Carleman estimate distributed in omega epsilon. So what we'll do is that we will consider a Carleman estimate on the boundary first. We start from the boundary. So we introduce this notation, I of S lambda phi, which is, okay, weighted, this is weighted L2 norm with the good exponents. So you have exponential 2s alpha phi cube. So you see, this is, well, when t is away from 0 and capital T, this is the L2 norm. But this degenerates near t equals 0 and near t equal capital T. And you have to multiply by the good powers of the good exponent of S and lambda. The same for the gradient. You have the, here you have, you have phi cube. Here you have phi. Well, the gradient, the L2 norm of the gradient, weighted by this guy, and with the exponent S lambda squared. And you have S minus 1. Well, this weight here, and here you can put the L2 norm of the derivative and the L2 norm of the time derivative and the second derivatives of phi. So we begin with the boundary Carleman estimate. And this is quite classical to obtain that. Well, this is quite classical for people who are familiar with Carleman estimates, which is not very, very common. Okay. You can do that with the pages of calculations, but there is nothing new here. So this quantity, you can prove that for S and lambda, large enough, okay, large enough, greater than S naught and lambda naught, for any S and lambda, there exists a constant which does not depend on S and lambda, okay? A constant C, such that this quantity is bounded by the weighted normal derivative of phi on gamma naught for any gamma naught and any t positive. Of course, this constant depend on gamma naught and depend on t. Okay, so we skip the proof of that, which is classical. Okay, now we want an observability inequality in omega epsilon for the distributed control. So we will prove that the quantity we have on the right-hand side of the Carleman inequality here, S lambda, this weight d phi d nu square, this is less than a term which we want, 1 over epsilon cube, something, a constant, phi square, a weight also, phi square, plus delta, for any delta positive, I S lambda. So of course, if you take delta sufficiently, if you have that, and if you take delta sufficiently small from this inequality here, you will have a plus delta I S lambda. You can take it on the left-hand side, and for delta sufficiently small, and we will have what we want, which is a constant phi square, a weight with a weight, and 1 over epsilon cube. Okay, so this part is long and technical. So if you don't want to follow what happens, just to go and have a drink while I'm doing that. Well, first of all, when we want to do that, first of all, we need to have a covering of the boundary and a transformation to local coordinates on the boundary. So for simplicity, so this is a completely technical, nothing very interesting. For simplicity, we omit this part and we will assume that gamma naught is a flat boundary. And we write x to be y on the tangential coordinate and z, the normal coordinate. And gamma naught is contained in z equals 0, and omega is contained in z positive. Okay. So with these conventions, we have minus d phi d nu. Nu is the exterior normal. So this is d phi dz, in fact, at z equals 0. And we introduce a positive cutoff function, which is C3 in 0, 1, which is 1 in 0 epsilon over 2, and 0 in epsilon 1. Okay? And which is the derivative is of the order epsilon minus 1, the second derivative of the order epsilon minus 2, and the third derivative is of the order epsilon minus 3. Okay. Well, in this situation, omega epsilon is contained in z between 0 and epsilon, of course. Okay. Well, now we write the normal derivative. This is the normal derivative of phi square with the good weight, z equals 0. Well, this is, of course, the integral of the derivative minus the integral from 0 epsilon of the derivative times when you take theta, because at time at z equal epsilon, theta of z is 0. Okay, so it is, and at z equals 0, theta of z is 1. So this is evident. And okay, you take the derivative of this guy, so you have 4 terms. First of all, sorry, I have a fly which is disturbing me. First of all, you take the derivative on theta z. Second of all, you take the derivative here, so you have minus 2 s square lambda exponential, the same exponential, but alpha z, okay? Third of term, you take the derivative on phi, so phi z, and the last term is you take the derivative on this guy, so you have minus 2 s lambda, you have phi z, okay? So you have the sum of 4 terms, A1, A2, A3, A4. Well, I did not notice that alpha z, well, I go back to alpha. So I have a problem with the pages. I go back to alpha. Okay. If you take the derivative of phi with respect to x, of course, or to x, you have lambda, the gradient of psi, times the same thing, times phi. And if you take the derivative of alpha with respect to x, you have the same thing. You have, this is 0, this is a constant, so this is 0. You have lambda, gradient psi, times phi, okay? Okay, so this is written here. Alpha z is minus lambda gradient phi gradient psi, and phi z is minus lambda phi gradient psi. So, for example, if you take this term, A4, you can bound it, you have a term in phi z square and a term in phi z square. But you have to take yes, there is something missing here. It is an s minus 1. So this is less than, for any delta, this is less than c delta s cube lambda square exponential s alpha phi cube. Here you have phi 3 over 2 multiplied by phi minus 1/2. Okay? So when you take Jung, you have phi cube, and here you have phi minus 1. Here you have phi z square, phi z square, but there is an s minus 1 missing here in the last term. So, okay, this is for this term. Okay, this and this will be treated in the same way as this one. You have phi z square, you have phi z square here, phi z square, phi z square. So the term, and theta, okay? The term which is the worst is this one, the first one, A1, theta z. So what do we do with A1? So in A1, we take an integration by part. We write phi z square as phi z, and we take one integration by part in phi z. Okay? So we integration by part, we obtain, so we take one derivative, we take one derivative of phi z, of phi to the other terms. So you have the derivative of e to the s alpha, 2s alpha, which gives you this one, phi z, theta z. You have the time derivative, the sz derivative of theta z. You have the derivative of phi here, phi z, theta z, and we have the derivative of what? Of phi z, which is phi z. And again, this is the sum of 4 terms. For this one, this one, this one, this one. And here we will use again integration by parts, except for this term. Here you have phi z, which is 1/2 of d over dz of phi square. Again, here phi z is 1/2 d over dz of phi square. And here phi z is 1/2 d over dz of phi square. So B1, okay, no, this one we don't need. We don't need because it is in epsilon -1. And you have phi and phi z. So this one we don't need. We can bound it immediately by something in phi square, phi z square, and something in phi square with c delta and delta. So this is a term in phi square. This is what we want. And here we have epsilon -2 because we have theta z square. Okay, so this is epsilon -2. And epsilon -2 is better than epsilon -3, of course. For B2, we use this integration by part. Phi z is d over dz of phi square. So we integrate by parts, and we have a term in theta zz, a term in phi z. Well, sorry for the tech. The term in phi z, and theta zz, and a term in theta triple z, okay? Z. So this will be in epsilon -3, okay? So this is less, this is in epsilon -2, this is epsilon -2, and this is epsilon -3. So this dominates, this term dominates the other ones. So this one is in epsilon -3, phi square plus weight. All the other terms can be estimated in an analogous way. So at the end of the day, you come up with the following. So you have what we want, the integral of gamma naught times 0t of d phi d nu square is less than a term in epsilon -3, this one, I don't remember why you have S7 lambda 4. Ah, yes, you have S7 lambda 4. Okay, whatever. We don't care about that. And we have, sorry, and we have a delta term phi z square and a delta term phi z square. And these guys are part of IS and lambda. So this is bounded by delta IS and lambda, which is written here. So taking the delta small, we obtain that IS of lambda is less than C epsilon minus cube. So I don't remember why you need S7 lambda 4. And you have this term here with phi square inside. Okay. Well, now we want to obtain from this Carleman inequality, IS and lambda has terms which degenerate near t equals 0 and near t equal capital T. Okay, near t equal capital T, it's okay. But t equals 0, we don't want that. So we change the weight. Instead of t capital T minus t, we take it for t between t over 2 and t, and we take t over t squared over 4 before t over 2. And we change the weight, gamma and beta, with, instead of having T, capital T minus T, we have L of T here. And now we use, well, remember that phi is a solution of a backward equation. Phi is a solution of a backward equation. So when you have the value at the final time, which is 0, because you go from T to 0, you can obtain it using what you have between 0 and T over 2, and then by a standard energy estimate. Okay? So now we take, instead of I S lambda phi, you have J of S lambda phi, which is the same, except that we have changed alpha in beta and phi in gamma. Okay? And we use classical energy estimates with a cutoff function, and we deduce the observability inequality, which is phi 0 square plus this quantity is less than the right-hand side. Okay, this is classical and is not difficult. Okay. So now we have our observability inequality, which is phi 0 square plus these terms is less than epsilon minus q, c constant epsilon minus q phi square in omega epsilon cross 0 t. So in order to simplify, we can take gamma star, the maximum in x of gamma, and beta star, the maximum in x of beta. And we can find the control using this inequality. Again, it is classical, to find a control which is essentially phi epsilon with 1 over epsilon cube because of the constant. And you take this weight for convenience, where phi epsilon is the solution of the adjoint problem, suitably chosen. And you can show that this solution, this phi epsilon converges to phi, which is also a solution of the adjoint problem. And now you come up with the heat equation with this right-hand side, 1 over epsilon cube, phi epsilon, this weight, okay, we don't care about this weight, concentrated in omega epsilon. Y epsilon is 0, the initial condition is 0, and we have at time t, y epsilon at time t is 0. And we have that this guy, phi epsilon, satisfies 1 over epsilon cube. This quantity is less than the initial constant times the initial condition square. Okay? Why that? Because you just multiply by phi epsilon, you you take the adjoint, you have phi epsilon, which is solution of the adjoint problem, and the only term which appears is y0 phi epsilon of 0, but phi epsilon of 0 is bounded by this term to the 1/2. So, okay, this is absolutely evident. And you have convergence of phi epsilon because of all these estimates to phi with the weights, okay? And phi is also, again, convergence is solution of the adjoint problem. Okay, so again, what happens to a problem like that? You can take, for those who are not interested, you take any good operator, minus delta, wave equation, heat equation. You take your right-hand side, which is regular, 0 on the boundary, concentrated on an epsilon neighborhood of the boundary, on a layer on the boundary, and singular of the order 1 over epsilon q. Okay, what happens? No way to obtain classical estimates. You cannot obtain estimates on y epsilon in H10 or L2 H10 or whatever. No possibility. Okay. So you have to take the weak formulation of this equation. So we have a heat equation with the right-hand side concentrated and singular. So we want to pass to the limit in the weak formulation of the control equation. So for the weak formulation, you take for any zt and any h in the good spaces, L2 of Q, we associate the solution of the adjoint problem, minus zt minus delta z equals h, 0 on the boundary, and z at time t equals zt. And the weak formulation for y epsilon, you multiply by h, you integrate by parts, and you obtain that the integral of y epsilon h dx dt is, okay, the right-hand side. H is minus zt minus delta z, so you integrate by part. So you have dt y epsilon minus delta y, which is this guy, times z, okay? And the only term which comes out of the integration by parts, because z is 0 on the boundary, y epsilon is 0 on the boundary, and you have the initial condition, which is y 0 at time x, y 0 of x, times z at time 0, because y at time t is 0. Y epsilon at time t is 0, okay? You have driven the heat equation to 0. Okay, this is the weak formulation. And now, okay, this term is constant, so no problem. So what about this term? So you have the weight, you forget about the weight. You have 1 over epsilon cube, the integral on the layer of phi epsilon z. Z is a good function. Z is a good function. Okay. So okay, again, z is a good function. So 1 over epsilon cube, the integral over the layer of z squared is bounded. And essentially, this is represented by the normal derivative of z. Well, and we can show, but this takes a lot of pages of calculation, we can show that all this term tends to 1/3 the weight on gamma naught on the boundary of d phi d nu dz du. Well, if everything were regular, if gamma naught is flat, if all the things are regular, you can just take expansions of phi epsilon, or phi, if you want phi, because the limit phi and z, you take z equals z of 0 plus, well, the normal component is z also, so it is not a good notation. Plus s times dz ds at 0 plus s squared, etc. And when you integrate in omega epsilon, you can see that, and you take the same for phi epsilon, and you will see that the 1 over epsilon cube give you exactly 1/3 of this term. But to do this correctly, you need a lot of calculation. And therefore, you can go to the limit in the weak formulation. So this term, again, is constant. This term is the limit of this term. And y is the limit of y epsilon. You have a limit y for any h. And this is a weak formulation. If you read that for any h, take z associated to h, this is this term, this problem. The heat equation with the right-hand side 0, non-homogeneous boundary condition here, minus 1/3 of the weight times d phi d nu on gamma naught, 0 on gamma minus gamma naught, initial condition, and y of t is 0. Because here, zt, the value of z at time t does not appear. So it is valid for any c, and you have that necessarily y of t is 0. Okay, so my time is almost over, and I thank you for your attention.
Thank you very much, Jean-Pierre. I don't know if there is a question or comments. I can start with one question, Jean-Pierre. In the technical proof, you assume that my question is, what do you know if the part of the boundary is not flat, you can do a change of variables? No, did you say that?
Well, yes.
There is some geometrical hypothesis do you need for the boundary?
No. I need a regular open set. I don't want to, but I need, of course, a change of coordinates near. We need a covering of gamma naught, and then a transformation to a flat boundary by change of coordinates. And we want to have the local coordinates, normal coordinates, and tangential coordinate. So go back to a flat boundary by a transformation. Well, this is, of course, I have the Jacobian, which enters and so on and so on. So this is more technicalities, which are done in the paper, but I don't want to, it was enough
of course.
Technicalities here.
Yeah, but you don't need nothing more than regularity. That's my question. Mm-hmm.
No, I don't need anything more. Okay. I need regularity, that's all.
Of course.
The regularity to have transformation and enough regularity to. Sylvain is asking a question.
Sylvain.
Yes, so thank you very much for your talk. I have a question. So do you use the Carleman parameters and S and lambda, or in fact you could do the whole proof with weight function exponential C over T and that's it?
I use the Carleman parameter to obtain the Carleman estimate. Okay, I use to obtain the Carleman estimate, and after that, I fix the parameter. I fix S and lambda. I don't need any use of Carleman of parameter S and lambda afterwards. Once I have the Carleman estimate, I fix S and lambda. I don't think they could be of any use. I don't think so.
But if you take the kind of observability estimate we see sometimes for the heat equation, where you have a weight exponential minus C over T minus T, and you start from that, can you still prove the same thing or not?
Sorry, I don't understand what you say.
So sometimes for the observability for the heat equation, you simply write that you can estimate your solution at time. So for, let's say, for the adjoint in the good sense of time, that you can estimate your solution at time t by the norm of the source term and the norm of the observation. So if you start from that, is that enough for you to conclude or not?
No. The problem is, well, if I start with the distributed control in omega epsilon,
Yes.
I have, well, I don't know any way to obtain a sharp constant C of epsilon.
Yeah, but okay.
In fact, what I do is I start with the
boundary control.
Boundary Carleman estimate. Boundary Carleman. Yes. And I prove that this is valid also for the distributed case. In fact, what we prove is that the boundary Carleman estimate, which means that you have a weight which is the gradient of the weight of basic weight is not non-zero everywhere in omega, even in omega bar, okay? And you have, you only need a negative normal derivative outside the region which of interest, okay? In order to have to get rid of the terms on this part. Well, so the Carleman estimate for the boundary is still valid for a layer around near the boundary, but it takes some time. And here you can prove that the constant is of the order epsilon minus q, which is optimal. I don't know how to prove that starting from the Carleman estimate, classical Carleman estimate. But in fact, I proved the Carleman estimate for the distributed control with the weight adapted to the boundary. Okay, that's all.
I completely understand.
That's what we do.
Okay, but I'm just saying that maybe Carleman estimates are not of real use. I mean, if you start from the observability estimate from the boundary for the heat equation, probably you would be able to do the same, right?
You take the observability inequality and not the Carleman estimate? No, well, maybe you are right, but I don't know how to do it, because when I estimate the L2 norm of the normal derivative on gamma naught, I have the good term, what the term I need, plus a delta times the terms which appear in the Carleman estimate.
Okay.
I don't know how, well, maybe it's just technical, I don't know. But I don't know how to prove directly that the normal derivative, you see that the normal derivative, the norm of the normal derivative square is bounded by 1 over epsilon cube, the integral of phi square. There are some rest terms, and the rest terms, you see, even if you want to expand everything in power, you have the rest terms, and the rest terms I can bound them by using Carleman estimate. So.
Yeah, sure.
But maybe we are not clever enough. That's possible. But what we did, we need the Carleman estimate.
Okay. Well, thank you.
There is another question. we have time, maybe Belacen.
Jean-Pierre, my question concerns the epsilon neighborhood of the boundary,
Yes.
omega epsilon. So you construct your sequence of controls, internal controls, on the omega epsilon
Yeah.
open set. And you let epsilon go to 0, and then you obtain a control on the boundary,
Yeah.
the part of the boundary which is the limit of the omega epsilon.
Yeah.
And you assume that omega epsilon satisfies uniformly with respect to epsilon the GCC condition, the geometric condition.
Yes. For the heat equation, we don't have a geometric condition.
No,
For the
no,
wave equation.
for the wave equation, exactly.
Yeah.
So you assume that omega epsilon satisfies this geometric condition. But what about the limit subset of the boundary?
No. I start.
On which you obtain your control, your boundary control.
No. I start with a part of the boundary which satisfies the geometric condition. I take an epsilon neighborhood of that, and this will satisfy necessarily. This will satisfy the geometric condition. Okay.
But the limit control you obtain on the boundary is not.
I don't know the converse. Maybe the converse is also true. If you take this layer, this union of balls of radius epsilon and so on, which satisfy the geometric condition for any epsilon, does the limit satisfy the geometric condition?
Oh, but it contains.
Yes, but anyway, I don't take it.
It contains the initial subset gamma 0 of the boundary. So surely it satisfies geometric condition on the boundary.
Yeah.
Since it contains the starting part, the initial part of the boundary.
Yes.
But the control you obtain is not given by Ashram method.
Why? The control?
This control is a limit of controls.
This control.
It doesn't come. It doesn't come
the
from
limit of control. Yeah.
Yes. It doesn't come from an observation from the boundary.
It does not come from an observation from the boundary. Yes. But I think it is. I think.
My question is it continuous with respect to the initial data?
Yes, it is continuous with respect to the initial data, but I think it is still
each internal control. Let us say f index epsilon is, of course, each internal control of the sequence is continuous with respect to initial data for the wave equation. At the limit.
At the limit, it is still continuous with respect to the initial data. This is sure, because you have the estimates, and you can pass to the limit in the estimates. No problem. No.
So the boundary is constant.
But is it the same? Is it the control that you obtain by HUM, by HUM? I think so, because you have the problem is that I think you have convergence. Well, the problem is the following: do you have strong convergence? Okay. Do you have convergence of this term 1 over epsilon cube, the integral on the controls on the layer square? Does this converge to 1/3 of the integral over gamma naught of the normal?
This is the question.
Of course, you have it is convex, so you can have semi-continuity, but okay. I think this term is bounded. and converges, and you can go to the lim-inf, but I think you, well, we did not prove that we have convergence of this term, but in fact, I think we have. I think we have. This is a good question. I think we have convergence of this integral, but okay. Okay.
Peut-être.
I cannot ask Caroline because she is there.
Okay, thank you. Thank you for the question. There was another question or no?
Enrique wanted to ask a question.
Enrique?
If we have time, just, well, at the end, you have used solutions by transposition, what you have called weight solution.
Yes, yes. Yes.
So I think that for a similar semilinear problem, it is not clear whether you get compactness in L2. So this is my question. Can you say something in a semi-linear context?
Okay. The only problem we treated were linear, but the question of nonlinear, semi-linear problems, I think we can do something. Of course, we can. First of all, we can put a right-hand side, but you know that if you put a right-hand side, you need conditions on the right-hand side to obtain zero. You cannot at the same time, you cannot want the solution to be zero and put a source term which drives it away from zero. Okay. So for the semi-linear case, you have to be careful of that. If you put the right-hand side, okay, you can use a fixed point method and so on, but well, if you take I think you. Well, for the Lipschitz case, I think you have you will have the same. Well, the problem is to have uniformity of the constants again, okay, with respect to epsilon, and the uniformity of the constants for the Lipschitz case, I would say I'm almost sure you can have that, but otherwise. Look, the question is the uniformity of the constant. After that, pass to the limit. Wait, you have to be careful that because the convergence cannot be strong. The convergence cannot be strong because you do not keep the boundary conditions. Okay, you do not keep the boundary conditions. So no way to expect a convergence in H1 or something which would say that you keep the boundary condition. So the convergence has to be weak. So have to be careful in passing to the limit in nonlinear terms. Okay.
That's the point. Yeah. Mm. Okay. Thank you very much.
Thank you.
Anyway.
Okay, if there is no more questions or comments, is James Leroy, the last question of the seminar. Okay, James.
Thank you for this amazing presentation. My question might seem somewhat basic, but I'm new to control theory. My question is that function psi that is used to the construction of your Carleman inequality. Do you have an example of such functions? I heard that Lyons have proved the existence of such function, but do you know?
No, not Lyons. Emanuelov or
I'm sorry, Emanuelov and the true Russian. Do you know, do you have the example of such function psi in your Carleman estimates?
Do I know what?
Do you have an example of yes?
Of course, in 0, 1, 0, okay. In 0, 1, omega epsilon is 0 epsilon, for example. So take a function psi, which is growing from 0 to, I don't know what, for epsilon minus 2, epsilon over 2. Then going back from epsilon over 2 to epsilon, not to 0. From epsilon over 2, you go back straight to 1 with a non-zero derivative. So you see, you go the only place where this function where the gradient or the derivative of this function vanishes is at the epsilon over 2. You just draw a function like this, okay, and okay, this is for 0, 1. When you have a set, an open set omega, which is complicated, well, when the set omega is convex, for example, no. Depends. It depends. No. It's not for a layer. For a layer, it's not easy to. When you have omega epsilon is in the center of a ball, you have like a chimney. You construct like a chimney, and then you cover the chimney on omega epsilon. For the case of a ball, it is really difficult, but you can to give explicit example is difficult.
Okay.
Rotate the previous one. But in fact, the weight I consider here in 0, 1, the weight I consider here is just it's 1 minus x.
Yeah.
Okay, you take 1 minus x, just a straight line, and this is okay for 0, 1, because I just want the derivative to be non-zero in the whole omega. And that's all. And the normal derivative to be negative outside gamma naught, which is 1. And the normal derivative is negative at 1. 1 minus x is minus 1. Okay. So on 0, 1, it is 1 minus x. On a complicated set, I cannot tell you an explicit weight.
Okay, that's good. Thank you.
Thank you, James. Okay, I think we arrived to the end of the seminar. So thank you, Jean-Pierre, for the talk. Thanks all the participants, and I will finish the online.
Thank you, and congratulations for your organization. I hope this